This is the third session on molecular geometry dealing with the VSEPR model. Remember, VSEPR model is valence shell electron pair repulsion. And what that means is the number of electron pairs you have around an atom repel each other, and they will determine certain shapes with or without bonding. And so far we've dealt with a molecule that was linear, and that was beryllium fluoride. And we discovered beryllium will take the shape of a straight line, linear. The problem with beryllium is it's in group 2, and it only has 2 valence electrons. When it forms 2 bonds, it's an exception to the octet rule because it only has 4 electrons totally around it, as is the next compound, boron trifluoride, we did in the VSEPR model 2. 3 pairs of electrons, these are all bonding, go to the maximum distance they can get away from each other. And this maximum distance, as you recall, was 120 degrees. It's called trigonal planar. Trigonal, a triangle, fancy word for triangle, and it's on one plane, planar. What we're going to deal with today are the most common 4 electron domains surrounding an atom, like carbon, and there'll be 4 hydrogens around it, and we're going to talk about that geometry. And so I think the first thing we have to do is clarify what this electron domain means. What is electron domain? Most important, domain is a spatial region. Electron domain, around the central atom, you can have it attached to other atoms through single bonds, by far the most common, single bonds, and you can have double bonds even. And most interesting, you could have an electron region with no bonds at all, but with a pair of electrons or more. The electron pair. We sometimes call that a lone pair. So let's start with methane. Methane has 4 valence electrons. 4 valence electrons. And if you bond that with its 4 atoms, you put carbon central when you have carbon. You can't put hydrogen central for several reasons. One reason, it only can form 1 bond, so you couldn't have it central. So you have 8 electrons being used in the bonds, you have none left. So what kind of shape do we have here? Here's carbon. We have 2 bonds on the plane, say of the paper. 1 bond comes out from the paper, 1 goes behind this paper. So what you have is a situation where the maximum distance these electron pairs or bonds in this case can get away from each other, which means minimum repulsion, is a very important angle that we will call the 109.5 degree angle, and that is a shape of a tetrahedral. Tetrahedral shape. So this is a starting point. Methane, CH4, is tetrahedral. Now let's go to a variation. Let's go to this molecule, ammonia. Ammonia is NH3. And we draw ammonia out. It's 1 nitrogen, 3 hydrogens. And if we take the 5 plus 3, we have 8 total electrons, 5 for nitrogen, 1 for each hydrogen. And you have 1, 2, 3 bonds, it's 6 electrons. You put the last 2 electrons around the outer atoms. Well, we can't do that. Hydrogen has the helium noble gas configuration already. So we put them on the central atom. Now, let's go over to the geometry. In this case, nitrogen is a central atom, and it has 1, 2, 3 bonds, and then it has a lone pair of electrons. And we'll just sort of draw that area there. It's not defined. In fact, there's a little push here of these electrons down on the bonds. So ammonia should be tetrahedral, 4 electron domains. 3 are bonding, 1 is non-bonding. The actual angles of this is about 107 degrees because of the repulsion here. 107 degrees, very close to tetrahedral. And the name is important. This is called, here's a triangle base. This is called trigonal pyramidal, P-Y, pyramidal. It's a pyramid with a triangle base. Instead of it's a 3-point base. It's a flat triangle. Let's take another one. Water, H2O. H2O. Well, we start right out. Oxygen has 6 electrons. Hydrogen has 2. That's 8 total electrons. If we draw the structure out, we have oxygen is central, surrounded by 2 hydrogens. Take the 4 electrons off from the bonding. This is 8. Subtract the 4, and we have 4 electrons left. So we put those on the central atom. And what do we have in the shape? We'll draw it over here. There's oxygen. There's a bond. There's a bond. And we have these 2 lone pairs of electrons. 4 electron domains again, but 2 are bonding. So these 2 push down on the bond. But the angle we have now is again, starts off with the tetrahedral, but it pushes down, and this you may or may not want to memorize, but it's just about a 105-degree angle. It starts with the 4 electron domains tetrahedral concept. This is called a bent molecule. Bent. And of course, very quickly, you could have something like HCl. Here you have 1 bond. You have 3 electron pairs unused, 3 electron domains, and of course this is just 2 atoms connected. That's a straight line. These have to be linear. But the point is there are 4 electron domains. 1's bonding, 3 are non-bonding. So what I recommend is, we'll stop right there, but you could go back and you can look at molecular geometry model 1 or 2, or go to the Lewis model. And this will end this session.